Okay, so today we're going to talk about graphing linear functions using their solutions. And we're back to the Integrated Algebra Learning Standards algebra, the algebra AG3. So it's a geometry standard within algebra. That's why we call it integrated algebra, because it's algebra with some geometry. So that standard is determine whether a relation is a function, which we talked about the other day, and examine ordered pairs and by examining ordered pairs and inspecting graphs. So we've looked at ordered pairs before in the last lesson, and we've determined whether or not they were a function based on the ordered pairs. But now we're going to look at graphs and see if they are a function by looking at graphs of relations. And the other thing that we're going to work on is we're going to graph and solve systems of linear equations and inequalities with rational coefficients in two variables. We're actually not going to solve systems yet, but we will talk about graphing linear equations. So it's sort of on our way to doing AG7. We're going to have to do today's lesson. How do we graph linear functions using solutions? We're going to talk about first degree equations. We're going to talk about standard form and a linear equation. Now let's say that I asked you to think of two numbers that add up to 6. Now if I said find an equation for the two numbers x and y, so you would write x plus y equals 6, right? Two numbers that add up to 6. This equation that we just wrote down is a first degree equation in standard form. First of all, it's first degree because the variable on the x is 1. Okay? A second degree equation would look something like this, where the exponent on the x is 2. Okay, so we look in particular for the x. We also look for the y. So all the variables here have exponents of 1. So we say it's a first degree equation. It's written in standard form. So there's a number of different ways you can solve this equation. If you have x plus y equals 6, you could have also written it as 6 minus y equals x, or 6 minus x equals y, right? So if you have two numbers that add to 6, then if you subtract one of them from 6, then you get the other one. Okay, but the way that we wrote it here, the x and the y on one side and the constant on the other side, we call 6 a constant because it doesn't have a variable associated with it. This is known as a first degree equation in standard form. So standard form is written so that the variables are on both sides and that there are coefficients to the variables and that these coefficients a and b are not 0. Okay, so another way I could write like another linear equation in standard form could be something like this: 3x plus 4y equals 8, right? We have x and y on both sides. X comes first, y comes second. We have coefficients for x and y that are not 0. We have a constant on the right side of the equation. Remember, the coefficients for the first one we wrote were 1. So we have 1x plus 1y equals 6. So if we were asked to find solutions to the equation and create a table, okay, so we could have a table with x and y. So let's say if x were 1, y would be 5, right? Because we want their sum to always be 6. That's the property that we have for this relation. All right, if I have 2, then I would have, if x were 2, y would be 4. Then 3 and 3, 4 and 2, and 5 and 1. I mean, I could also have 0 and 6. And I could also, I mean, I'm writing down whole numbers, but you can have numbers that are not whole numbers. If it were negative 1, if x were negative 1, I'd have to add 7 to negative 1 in order to get to 6, right? I could also have decimals. I could say, well, 2.5. I'd have to add 3.5 to 2.5 in order to get to 6. Now, if I look at the x and y pairs, okay, I would have 1, 5, 2, 4, 3, 3, okay, so there's tons of different pairs of numbers, more than tons. There's an infinite amount of numbers that I could choose for x and therefore have a y associated with that, right? I could choose 1.1, I could choose 1.2, I could choose 1.15, 1.16. There's lots of different numbers I could choose for x. And whatever number I choose for x, I'm going to get a particular y. Right? With 1.1, I'll get 4.9 or 4.8 and so on, right? So there's an infinite amount of coordinate pairs that are associated with the relationship between x and y such that x plus y equals 6. Now, if I were to graph the solutions to the equation, so all of these, by the way, all of these ordered pairs and the infinite amount of ordered pairs that I did not write down are members of the solution set of the equation. Remember, the equation was x plus y equals 6, right? So how many things fit as solutions? There's an infinite amount of things that fit as solutions, right? And if I were at the very beginning of the year, we talked about solution sets, right? We said that solution sets were the set of all ordered pairs that fit into this equation and make it true. So, 1, 5 would be an element of the solution set, 2, 4, and so on. Okay, remember we write sets with the curly brackets, and the elements of this set in particular are coordinate pairs. So if I were to graph all the solutions to the equation, so the ordered pairs are 1, 5, 2, 4, 3, 3. Let's graph those first. 1, 5 is right here. 2, 4, 3, 3. And what you're going to see is that this really nice thing happens where they all the points that are solutions to the equation x plus y equals 6, they all lie on the same line, right? This is 1, 5, this is 2, 2, 4, 3, 3, 4, 2, 5, 1, 6, 0, and then here I have the -1, 7, and so on. All of these solutions lie on the same line. So if I draw a line, and in fact, if I were to think about a point, like if I zoomed in and I found a point between any of the points that I have drawn, so let me just draw this in red, like this point right here, this point would still, it looks like it's on the same line. If I found the coordinates of that point, that would be, it looks like it's about 4.5, 1.5, 4.5, 1.5, and you'll see that again they obey the same relationship, x plus y equals 6. So there's this really nice thing that happens when I look at solutions to this equation, x plus y equals 6. They all lie on this nice line. Okay, so if I draw a line between all the points that I have here, this line, this red line that I've drawn, is a picture or a graph that describes this relation, okay, the x plus y equals 6 relation, where if I take the first coordinate and I add to the second coordinate, the sum of them are 6, right? So if I have an x and y pair, all the x and y pairs along this line have that property. So like if all these little tiny x and y coordinates that make up this line, right? Like a line is made up of infinite amount of points, and points that are so densely clustered that they look to our eyes as if they are a line, right? So there's an infinite amount of tiny little points on here, and every single one of those points have that property where if you take the x coordinate and you add it to the y coordinate, the sum is always 6. Okay, so it's a really nice result that we get here. It's a nice way of looking at a relation as both it has an algebraic component where I can write an equation. It also has this geometric component where I can draw a picture that describes this relation. And being able to draw a picture is sort of a nicer way of figuring out how to compare different relations. Like if I looked at the relation x plus y equals 7. Okay, and I'm trying to compare it to x plus y equals 6. Well, some points on x plus y equals 7 could be, 1, 6, this point right here, 2, 5, okay, that point right there, and actually all the points are going to lie along this line. So it's going to be almost identical, but it's going to be shifted up by it's translated upward by one, diagonal unit. Right, so this is, actually it's just translated by one vertical unit, really, because look at the difference between this line. These differences always one space apart. So it's a nice way to compare this. I can compare these relations by looking at the equations, or I can compare the pictures of them. I can say, okay, the lines are almost identical. It appears to have the same, inclination, the line does, the green and the red line, but the green line is 1 unit above the red line. It's always 1 unit above the red line, which makes sense because your x and y coordinate pairs on the second one add to 1 more than the x and y coordinate pairs of the first one. Okay, so and types of questions that you should be able to answer. Does the point 2, -3 lie on the graph x minus 2y equals -4? So you might want to pause the video and see if you can try to think this through yourself, because right now you have all the things that you really need in order to answer this question. Okay, if the point, what would the point look like if it lied on this graph? Okay, and one more thing, let me just go back and explain something very quickly. All the solutions, let's just look at the red line for a minute. All the solutions to the equation x plus y equals 6, every single thing that could possibly, every single pair of numbers that could possibly be added together to get 6, lie on this red line. Okay, so every single point on this red line is a solution to this equation, and every single point that's not on the red line, all these points in the xy axis, x and y plane here, all the points that are not on the red line do not have this property. Okay, so if it's on the red line, they're solutions to the equation. If it's not on the red line, they are not solutions. So that might help you answer this question. Does 2, -3 lie on the graph x minus 2y equals -4? And by this equation right here is an equation in standard form, because we have, if I wrote it like 1x plus -2y equals -4, well, here we have our ax plus by equals c, right? So our a would be 1 here, our b would be -2, and our c would be -4. So just, this is a linear equation written in standard form. Okay, I say that because there's going to be other ways that we write linear equations other than standard form. So so if this point 2, -3 lies on the graph of x minus 2y equals -4, if it lies on the graph, it must be a solution. So if it lies, this is the logic. If it lies on the graph, it has to be a solution to the equation. It has to be a solution. Okay? Because if it weren't on the graph, then it wouldn't be a solution. We just went over that. Everything on the red line was a solution to the equation x plus y equals 6. Everything that wasn't on the line was not a solution. Okay, well, if it's a solution, then I should be able to substitute the x in for that x and that particular y in for that y and come up with a true statement. So is it true that 2 minus 2 times -3 equals -4? Okay, so let's do a little keep change here. 2 plus -2 times -3 equals -4. 2 plus -6 equals -4, and that is true. -4 is equal to -4. Okay, that's a true statement. So my answer is yes. This point 2, -3 lies on that graph because it's a solution to that equation. Okay, so somewhere on the graph of this equation, wherever it is, if it's that line, it's this line, or this line, this point will lie on that line. I guess I know a point that it goes through, right? So it'd be 2, -3. So whatever line it is, the line has to go through that point. Okay, now another question that you could see is, what is the value of D if this point, D, 4, lies on this line? So you also, again, you can pause the video, see if you can figure this out yourself, because it's kind of a nice question. So I know that if this point, D, 4, lies on the line 3x plus y equals 10, then it must be a solution to that equation. So let's put the 4 in for the y and see what x has to be in order for this to be a true statement. Okay, so I just substituted 4 in for y into the linear equation in standard form, and now let me solve this for x. So 3x must be 6, so that must make x equal to 2. So D would have to be equal to 2 so that the point D, 4 would become 2, 4. And then this point is a solution to that equation, so it lies on the line of that equation. Okay, so here's another thing that you might be asked to do. Write the following verbal sentence as an equation. The sum of twice the x-coordinate of a point and the y-coordinate of that point is 4. So if I look at an xy coordinate, the sum of twice the x-coordinate, so twice the x-coordinate, the sum of that and the y-coordinate is 4. Okay, so here's my equation, 2x plus y equals 4. If I were to ask to draw this equation, what does this equation look like on a graph? What I could do is come up with some xy pairs and make my line. So if x were 1, I'd have 2 plus y equals 4. So y must have to, so it'd be 2 times 1 plus y equals 4. So it's 2 plus y equals 4. Y must be equal to 2. So let's graph that 1, 2. Okay, that's a solution. Let's pick another one, 2. So we have 2 times 2 plus y equals 4. So 4 plus y equals 4. The only thing that's going to do that is if y were 0. Okay, let's try 3 here. So let's graph 2, 0. So here's my xy pairs, 1, 2, and 2, 0. If I put 3 into that equation, if I put 3 into that equation, I'd have 6 plus y equals 4. The only y that's going to make that work is a negative y, so it'd have to be negative 2. So 3, negative 2 is also one of them. So 3, negative 2 is right here, and you can see already these 3 points are what we call collinear. They lie along the same line. And in fact, if I found some other points that lied on that line, actually, I want to sort of go up in the same. I can find some more points by making these similar triangles right here. Right, all these points lie in the same line. If I wanted to find another point, I'd have to go up 1, 2, and over 1. There's another point that lies on that line. Let's check that point. This point right here is 0, 4. Is it true that twice the x-coordinate plus the y-coordinate plus 4 equals 4? That is true, because that would be 0 plus 4 equals 4. So that's true right there. Does that point match that? That would be negative 1, 6. 2 times negative 1 plus 6 equals 4. That's true. Okay, so all these points that, and all the points in between the points with integer values as x and y coordinates, all these little tiny points, all of these have the same relationship between their x and y coordinates. Okay, every one of these, if I picked it up, I found the x and the y coordinate, the relationship would follow that 2 times the x coordinate plus the y coordinate equals 4. And that's what it means to be on that line. It means that every x and y coordinate is a solution to that equation. And furthermore, it means if a point's not on that line, it means that it's not a solution. I know if I found the x and y coordinates at this point that they would not make this equation true. Okay, finally, if you are shown a graph of a relation and you're asked whether or not it's a function, remember, a function, we defined it with ordered pairs. We said that as long as the ordered pairs did not have the same x-coordinate, or if they did have the same x-coordinate, then they had identical y-coordinates, that it was a function. So in this case, if I look at these 3 ordered pairs, 1, 2, 1, 3, and 1, 4, these do not make a function. This relation is not a function because 1 would be sent to 2, but 1's also sent to 3, and 1 would also be sent to 4. So if you have 1 in your domain and 2, 3, and 4 in your range, that's a confusing rule. That's not a rule that would be a function. That's not a function rule. A function rule sends 1 to only one spot. If you had another number, you can send it to another spot, and so on. But now the graphs of relations that are functions, right? These are all graphs of relations. There's 5 graphs here, and I'll pull the. Hopefully, you can see this last one on the bottom here. The relations that are functions, obey a particular rule, and it's called the vertical line rule or the vertical line test. And this test is if you take a vertical line at any point, this is not a nice vertical line, it's not very straight, but if you take a vertical line and you bring that line across the graph, it never hits the graph of the relation more than once. So right here, this red line is intersecting the purple line only once. If I drew another vertical line, it would only intersect it once. drew another vertical line, it would only intersect it once. So this relation right here passes the vertical line test because for any given vertical line, it only intersects the purple line once. Okay, so if I were to ask if this were a function, the answer is yes, this is a function. Same with this curve right here that we call a parabola. If I draw a bunch of vertical lines, they always only intersect the graph at one point. Okay, so yes, this is a function, right? So this is a function. If I look at this circle, this green circle, it is a relation, but it's not a function, because if I draw out this vertical line in particular, it intersects it twice. So that's a problem. You can only intersect it once here. And what's happening in this case is that if you looked at the x and y coordinates for this top point, and you look at the x and y coordinates at this bottom point, since they both are those points are the same distance away from the origin along the x-axis, they would have the same first coordinate. So if I look closely at this, I could tell you that the points are like right here and right here. The points are 2, 3, -3, and 4. And here that point is -3, -4. Remember, we said that if they have the same x coordinate, then it cannot be a function. Okay, so if you look at the ordered pairs, you can tell because they have the same x coordinate. If you look at a vertical line, you can tell because it intersects it twice. It intersects the graph twice. So no, this is a relation, but it's not a function. Now this horizontal line is pretty nice. Okay, because look, any vertical line will only intersect the horizontal line twice. So this ends up being a function. So yes, this is a function. And at the very bottom here, hopefully you can see it, I have a vertical line. Okay, so let me just... Okay, so I just reproduced the graph so that you would be able to see it. So my question is the green line a graph of a function? Now, if I take a vertical line, so let me just start to draw some vertical blue lines. Okay, so far, these blue lines are not intersecting the green line at all. Okay, but then as soon as if I draw a vertical line that's right on top of the green line, not only does it intersect it once, it intersects it an infinite amount of times. So it's intersecting all along these points. All these points that share in common that they're on the green line and the blue line. So a vertical line is not only is it not a function, it's really, really not a function. I mean, that doesn't really make any sense because things are either a function or not a function, but this is the furthest away from a function you can be because it doesn't just intersect it twice like the circle did. It intersects the vertical line an infinite amount of times. So no, a vertical line is absolutely not a function. Okay? So that's the end of the lesson for today. You learned how to look at a graph and tell whether or not it's a function. And you also learned how to take an equation and graph the solutions to the equation and then looking at the line and comparing it to other lines.